In this section of logic, we're going to be looking at several different topics, including what a tautology is, what DeMorgan's laws are, as well as valid arguments or valid reasoning. So let's start out with a simple concept called a tautology. A tautology is going to be an example where we end up with having all truths. So, for example, P or not P would always end up being true. So, today is Tuesday or today is not Tuesday. Well, we would accept that as always being true. Now, we can prove that using a truth table again. Remember, for P, we only have two scenarios, true or false. So for not P, that would be false or true. And then, of course, for the final result that I'm looking for, P or not P, I'm evaluating the disjunction or. True or false is true, false or true is true. I would end up with all truths. And of course, if we have things that involve P's and Q's, we would have 4 lines there. And if all 4 lines end up being true, it's called a tautology. Now let's look at another topic called DeMorgan's laws. Augustus De Morgan was a mathematician that was involved in several different topic areas, including logic world as well as sets and Venn diagrams. DeMorgan's laws simply are this. If I have the negation of P or Q, where I would need to evaluate the disjunction first and then negate it, that will be logically equivalent to the negation of P and the negation of Q. So here's how I think of this. If I've got this as kind of my arrow, the negation, and I want to shoot that negation through there, not only will I hit into the first one and the second one, I'll flip over the deal in the middle. So it's kind of like Robin Hood shooting through there. And so the negation of the quantity P or Q would be the negation of P and the negation of Q. So it flips over the sign in the middle as well. We can prove this using truth tables and logical equivalence, as I covered in a previous video. The other DeMorgan's law that we have is the negation of the conjunction P and Q will be logically equivalent to the negation of P. Once again, if I'm shooting this through there, I get this guy, I flip this over in the middle, and I get this guy. So 3 with 1 shot. The negation of the conjunction would be the disjunction of the negations. In other words, not P and Q is logically equivalent to not P or not Q. So let's look at an example. Typically, if I say it is not the case that, everything I say after that is considered to be negated. So in this case, I could say, it is not the case that today is Tuesday or we have a quiz is going to mean the same thing as today is not Tuesday and we do not have a quiz. Okay? So that's an example of DeMorgan's laws. Now let's move along to valid arguments, sometimes known as valid reasoning. Valid reasoning and valid arguments say that the conclusion that we come up with must follow unavoidably from the hypothesis. Or if we have multiple hypotheses, more than one hypothesis, it's called hypotheses. So that's why I put that there. There are several examples that follow unavoidably that we actually have names for. Otherwise, we need to do things like truth tables or what's called Euler diagrams or Venn diagrams to help try and show proof. So we're trying to show validity, in other words, saying that, hey, the conclusion must be the case. Let's look at a simple example called modus ponens. Modus ponens, so I'll put a 1 here because this is the first example, of something, of an argument that is valid. Modus ponens is actually a Latin term for direct reasoning. So what is direct reasoning? This starts out with a conditional statement. So we have our first hypothesis, I'll call it hypothesis 1, would be if P then Q. And then our second hypothesis, hypothesis 2, says we also have P. And then our conclusion that we're going to come up with, which this line means therefore, or we could use 3 dots to say therefore. That's math shorthand for therefore. We can conclude Q. So I'll give you an example. if I say, if today is Tuesday, then we have a quiz. Today is Tuesday. Therefore, what are you guaranteed to have? We have a quiz. Okay? The conclusion will have to follow unavoidably. Now the question would be, while that makes sense, this is a fairly simple argument that we know ends up being valid. How can we prove that this is valid no matter what P and Q are? P might be, I might say, if today is sunny, then we'll go to the park. Today is sunny, therefore, we can conclude that I'll take the kids to the park, correct? Okay, so how do we prove this, that it has to be the case? Well, one thing is to think about hypotheses are things that we typically assume to be true, whether they are or not, okay? And then the conclusion is what we end up with. So we can do several different methods here. One is using a truth table. So we have if P then Q. In other words, we want to look at the truth of hypothesis 1 and hypothesis 2. Does that guarantee or imply the conclusion? So this is what we can look at. By the way, if I have 3 hypotheses, I can say hypothesis 1 and hypothesis 2 and hypothesis 3. Does that imply or guarantee the conclusion? And we can do a truth table evaluation of this. So once again, we always set this up with every possible combination of truths and falses. And then we'll say the first hypothesis is if P then Q. And hypothesis 2 is P. Now why did I put parentheses around the if P then Q? Because otherwise I would have evaluated the conjunction first. Does this imply or guarantee our conclusion Q? Now, I would consider the and before the last implication because of order of operations. But what you might do for visual separation is put brackets around that are dashed because I don't really need those brackets because I would evaluate this conjunction before the final conditional. And what I want to do then is I want to look at the final truth values for all those conditionals. And if I get always true or a tautology, then my argument will be valid. So let's go ahead and do this, and once again I will do it shorthand. Do order of operations. I got to do parentheses first. So the first parenthesis, the first hypothesis, I need to evaluate the truth there. If P then Q, straight truth table definition of that connective, true, false, true, true. And P. Now I'm just going to rewrite P here. P was true, true, false, false, false. That's P, right? And I'm going to take the conjunction of those two. So remember, for an and, the only way it's true is if both parts are true. It's harder to satisfy an and statement. So true and true is true, false and true is false, true and false is false, true and false is false. So guess what? I can get rid of those now. And so the left side of the conditional now is true, false, false, false. Now I'm going to take the implication of that with Q. Q is going to be this column here. So it's the green implies this column. And so what I'm going to do, I'm just going to rewrite Q over here to make it a little easier. Hopefully you can see this. But true, false, false. Okay? And then I'm going to evaluate the truth. So, if true then true is true. If false then false is true. If false then true is true. If false then false is true. Remember, if false then anything is true. The only way a conditional statement is false is breaking the promise. If true then false would be false. So what do we notice? Now I'm done with those. My final result here is a tautology. That means that having these two hypotheses, hypothesis 1 and hypothesis 2, does always guarantee my conclusion Q. I have a tautology. Therefore, modus ponens or direct reasoning is a valid argument because it winds up with a tautology.